Photonics is a multidisciplinary field that deals with the generation, control, manipulation, and detection of light. Here are the key points. Light as both wave and particle. Light exhibits a dual nature known as wave-particle duality. This means that it behaves both as a continuous electromagnetic wave and as discrete particles called photons. Photons are the fundamental units of light, carrying energy and momentum. They have no mass but travel at the speed of light. Applications and technologies. Generation. Photonics involves creating light sources, such as lasers and LEDs. Lasers, in particular, emit coherent light with specific wavelengths. Detection. Detecting light involves using sensors, photodetectors, and cameras to capture and measure photons. Manipulation. This includes changing the properties of light, such as focusing, steering, or modulating it. Transmission. Optical fibers play a crucial role in transmitting information over long distances using light pulses. Amplification. Devices like erbium-doped fiber amplifiers boost weak optical signals. Switching. Photonics enables fast switching of light signals, essential for optical communication networks. Sensing. Applications range from environmental monitoring to medical diagnostics. Historical context. The term photonics emerged in the late 1960s. It aimed to use light for functions traditionally associated with electronics. Key inventions include the maser, 1958, laser, 1960, laser diode, 1970s, and optical fibers, 1970s. These innovations laid the groundwork for telecommunications and the Internet. Scope and impact. Photonics spans a wide range of applications. Telecommunications, fiber optic data transmission revolutionized communication. Manufacturing, laser cutting, welding, and 3D printing. Biomedical, imaging, therapy, and diagnostics. Displays, LCDs, OLEDs, and projectors. Quantum technologies, quantum communication and quantum computing. Current developments in silicon photonics hold promise for further growth. In summary, photonics combines classical and quantum physics, engineering, and materials science to harness the power of light. It's a field that continues to shape our modern world. Ultrafast second-order nonlinear photonics. Researchers have explored nonlinear optical phenomena beyond the classical regime. From classical physics to non-Gaussian quantum dynamics, this area investigates ultrafast processes involving second-order nonlinear interactions. Applications include quantum information processing and novel light sources. 1. Liquid photonic devices. Liquid crystal lenses, beam deflectors, and prisms have gained attention. Microfluidics, electroeting, and dielectrophoreses offer dynamic control over light. These devices find applications in adaptive optics, displays, and imaging too. Metamaterial integrated photonics. Aluminum nitride photonic integrated circuits have emerged. These circuits span piezo-optomechanics and nonlinear optics, enabling compact and efficient devices. 3. Photonic topological insulators. In 2013, the first photonic topological insulators were demonstrated. These materials exhibit topological properties that protect light propagation against defects and disorder. Applications include robust waveguides and novel optical components. 4. Photonic crystal fibers. These fibers feature a periodic arrangement of air holes along their length. Researchers have achieved unprecedented control over light propagation. Applications range from telecommunications to sensing and imaging. 5. These breakthroughs continue to shape photonics, impacting communication, sensing, and quantum technologies. Photonic topological insulators, PTIs, have opened up exciting possibilities in photonics. Let's explore some practical applications. Waveguides and circuitry. PTIs enable backscatter-free waveguides, even around sharp bends and structural defects. Photonic circuitry can benefit from PTIs, reducing dependence on isolators and enhancing signal routing efficiency. 1. Slow light immunity to disorder. PTIs exhibit robust topological states that are insensitive to disorder. Slow light propagation through PTIs remains stable, making them valuable for communication systems. 2. Photonic chips. Photonic chips, which process data using photons instead of electrons, can benefit from PTIs. PTIs guide light around defects, improving chip performance and data routing for 5G and beyond. 3. In summary, PTIs offer novel ways to manipulate light, enhance communication, and create robust photonic devices. Certainly, let's compare photonic topological insulators, PTIs, to traditional waveguides, propagation mechanism. Traditional waveguides, these rely on total internal reflection to guide light along a specific path. The refractive index contrast between the core and cladding ensures confinement. PTIs use topological properties to guide light. They are immune to backscattering and defects, allowing robust propagation even in complex structures. Robustness. Traditional waveguides susceptible to scattering due to imperfect ions, bends, and disorder. PTIs highly robust against disorder, making them ideal for integrated photonic circuits and communication systems. Bending and curvature. Traditional waveguides sensitive to sharp bends and tight curves, leading to losses. PTIs can guide light around sharp bends without significant loss, thanks to topological protection. Applications. Traditional waveguides, widely used in fiber optics, planar waveguides, and optical communication. PTIs, emerging applications in chip-scale photonic devices, slow light systems, and quantum photonics. In summary, PTIs offer unique advantages in terms of robustness and flexibility, making them an exciting area of research and development in photonics. Photonic topological insulators, PTIs, have remarkable properties, but they also come with certain limitations. Structural size. One drawback is related to the size of structural variations in PTIs. These variations need to be at least half the wavelength they manipulate. Larger structural features can make PTIs bulky and limit the range of wavelengths they can effectively target. 1. Platform constraints. PTIs are often engineered using photonic crystals and metasurfaces. The choice of materials and fabrication techniques can impose limitations. Researchers must carefully consider the available platforms for realizing PTIs. 2. Practical implementation challenges. Achieving robust PTIs in real-world devices requires precise control over material properties. Fabrication. Imperfect ions, losses, and non-ideal behavior can impact performance. Overcoming these challenges is an ongoing area of research too. Despite these limitations, PTIs remain an exciting field with immense potential for revolutionizing photonics and waveguiding systems. Photonic topological insulators, PTIs, offer robust protection for light propagation, but there are other approaches as well. Let's explore a few. Photonic topological insulators, PTIs. PTIs are materials with topologically protected edge states that allow light to flow along their boundaries without scattering or losses. They are inspired by condensed matter physics and have been realized experimentally in various systems, including helical waveguides and resonator arrays. 1. Regular structural variations. Scientists have designed photonic structures with regular variations, leading specific wavelengths of light to flow along their exterior without scattering. These materials achieve topological protection, even around corners and imperfect ions. 2. Microring resonators, photonic crystals, and waveguide arrays. Researchers explore various nanophotonic platforms to achieve non-trivial topologies. Microring resonators, bidimensional photonic crystals, nanoparticles, and waveguide arrays can all contribute to topologically protected transport. 3. Quantum walks in photonic networks. Quantum walks in photonic lattices exhibit rich physics and exponential speedup for certain algorithms, for example, boson sampling. While photons themselves don't need protection from decoherence, topological photonic systems can still protect quantum information. 1. In summary, topological protection in photonics is a fascinating field with diverse approaches, each offering unique advantages for robust light propagation and quantum information processing. Quantum walks in photonic networks are fascinating phenomena that combine quantum interference and random walk behavior. Let's explore how they work. Discrete time quantum walks, DTQWs. DTQWs are quantum analogs of classical random walks. In a DTQW, a walker moves through a lattice or graph, taking discrete steps. At each step, the walker undergoes a coin operation, akin to a coin flip, that determines its direction. Photonic implementations. Spatial multiplexing. Photonic DTQWs can be implemented using spatial multiplexing techniques. These involve encoding different parts of the walker onto spatial modes of photons. Time multiplexing. Alternatively, time multiplexed DTQWs use temporal modes to encode the walker's states. Applications and exploration. DTQWs allow exploration of geometric and topological phenomena. They model processes like excitation transfer, energy transport, and multipath interference. PTIs, photonic topological insulators, can be used to simulate DTQWs and study non-trivial effects. Recent advances. Researchers have achieved strongly interacting photonic quantum walks using single-atom beam splitters. These advances explore correlated many-body physics of light, going beyond non-interacting photon models. 1. In summary, photonic quantum walks offer a versatile platform for understanding quantum interference, simulating complex systems, and potentially advancing quantum computing. In the context of quantum walks, single atom beam splitters play a crucial role. Let's explore how they work. Background. Quantum walks are analogous to classical random walks but involve quantum interference. Photonic quantum walks explore the behavior of one or a few photons in a given structure. Most photonic quantum walks use linear beam splitters, which lack photon-photon interactions. Strongly interacting quantum walks. Researchers propose a strongly interacting discrete-time photonic quantum walk using a network of single-atom beam splitters. These beam splitters involve individual atoms that interact with photons during the walk. Unique phenomena. For the case of two photons, the quantum walk exhibits strongly correlated transport. The walk can show either boson-like or fermion-like statistics, tunable by post-selecting the two-photon detection time interval. It can also sort different types of two-photon bound states into distinct output ports under certain conditions. Experimental realization. The proposed realization involves time-multiplexed synthetic dimensions. In summary, single-atom beam splitters enhance photonic quantum walks, allowing exploration of strongly correlated quantum many-body states of light. Synthetic dimensions are a fascinating concept that extends the effective dimensionality of physical systems beyond their apparent geometry. Here's how they work. Basic idea. Imagine a wave function defined in specific degrees of freedom, such as spatial coordinates or internal states. Synthetic dimensions introduce an additional dimension that doesn't correspond to physical space but rather to internal states or other properties. This extra dimension allows the wave function to take a different form, effectively living in a higher dimensional space. Applications. Atomic physics. In atomic systems, internal states, like Zeeman sublevels, serve as synthetic dimensions. Quantum optics and photonics. Photons can also exploit synthetic dimensions based on transverse modes or angular momentum states. Quantum simulators. Researchers design quantum simulators using synthetic dimensions to mimic curved spaces, artificial gauge fields, lattice gauge theories, twistronics, and even quantum random walks. 12. In summary, synthetic dimensions provide a powerful tool for exploring novel physics and engineering versatile quantum systems. Quantum simulators using synthetic dimensions are powerful tools for exploring complex quantum systems. Let's dive into the details. What are synthetic dimensions? Synthetic dimensions extend the effective dimensionality of physical systems beyond their apparent geometry. They introduce additional dimensions that don't correspond to physical space but rather to internal states or other properties. These extra dimensions allow wave functions to take different forms, effectively living in higher dimensional spaces. Applications and platforms. Atomic physics. Internal atomic states, for example, Zeeman sublevels, serve as synthetic dimensions. Quantum optics and photonics. Photons exploit synthetic dimensions based on transverse modes or angular momentum states. Quantum simulators. Researchers use synthetic dimensions to mimic curved spaces, artificial gauge fields, lattice gauge theories, twistronics, and quantum random walks. Recent progress. Researchers have made significant progress in studies of synthetic dimensions. Platforms include cold atoms in optical lattices, photonic systems, Rydberg atoms, and more. In summary, synthetic dimensions provide a versatile tool for understanding quantum matter, simulating exotic geometries, and advancing quantum technologies. Let's dive into the fascinating world of photonic chips. Definition and basics. Photonic chips, also known as integrated photonic circuits, are miniaturized devices that manipulate light, photons, on a chip-scale platform. They serve as the optical counterparts to electronic integrated circuits, ICs. Instead of electrons, photonic chips process and transmit information using photons. Components and building blocks. Waveguides. These are the fundamental channels that guide light within the chip. Waveguides can be made from silicon, silicon nitride, or other materials. Modulators. Photonic chips use modulators to control the intensity or phase of light. Electro-optic or thermo-optic modulators are common. Detectors. Photodetectors convert incoming photons into electrical signals. Filters and splitters. These components separate or combine different wavelengths of light. Light sources, lasers or LEDs provide coherent light for transmission. Advantages. Miniaturization. Photonic chips pack complex optical functions into a tiny footprint. High data rates. They enable high-speed data transmission, essential for telecommunications and data centers. Low power consumption. Photons experience minimal loss and consume less power than electrons. Integration, multiple functions, for example, modulation, detection, routing, can coexist on a single chip. Applications, telecommunications, photonic chips power fiber optic communication networks. Data centers, they handle massive data flows between servers. Sensing and imaging, photonic chips find use in environmental monitoring, medical imaging, and LiDAR systems. Quantum photonics, quantum photonic chips are emerging for quantum communication and computation. Challenges and future directions. Losses, reducing optical losses remains a challenge. Integration complexity, integrating diverse functions while maintaining performance is an ongoing area of research. Quantum photonic chips, developing robust quantum photonic chips for practical applications. In summary, photonic chips are at the forefront of modern technology, enabling faster communication, efficient data processing, and exciting quantum advancements. Photonic chips, also known as photonic integrated circuits (PICs), are essential for various applications in communication, sensing, and imaging. Let's explore how they are fabricated. Designing a PIC. The process begins with defining the chip's purpose and specifications. A chip architect collaborates with the customer to understand requirements and conditions for chip usage. Specifications set performance targets for the PIC design. Function blocks. The design team creates a schematic circuit diagram that captures the PIC's function. Functional blocks include lasers, modulators, detectors, and other components that manipulate light. Some blocks may already exist, while others need to be built. Simulation. Accurate prediction of chip behavior is crucial due to the cost and time involved. Simulation tools model the behavior of functional blocks. The goal is to ensure the chip performs as expected after manufacturing. Fabrication steps. The actual fabrication involves several key steps. Material growth or deposition, grow or deposit the chip material. Pattern printing, print a pattern on the material. Etching, etch the printed pattern into the material. Surface preparation, clean and prepare the surface. Repeat steps 1 to 4 as needed. 1. Applications. Photonic chips power fiber optic communication networks, data centers, and quantum photonic systems. They enable high-speed data transmission and efficient light manipulation. In summary, photonic chip fabrication involves design, simulation, and precise manufacturing steps to create compact and powerful devices for photonics applications. Let's explore the fascinating relationship between photonics and quantum computing in detail. Photonic quantum computing. Photonic quantum computing refers to using photons, particles of light, as the physical system for performing quantum computations. Photons are ideal for quantum systems because they operate at room temperature, and photonic technologies are relatively mature. 1. Advantages of photonic quantum computing. Scalability. Photonic systems can be highly scalable due to their compatibility with existing optical communication networks. Low noise. Photons experience minimal environmental noise, making them suitable for long-distance quantum communication. Interference and entanglement. Photons can be easily manipulated to create interference patterns and entangled states, essential for quantum computation. Photonic quantum algorithms. Researchers have developed quantum algorithms based on photonic states, such as squeezed light. Squeezed light allows for efficient sampling algorithms that outperform classical computers in specific tasks. Applications include simulating molecular transitions and molecular docking. 2. Photonic quantum hardware. Photonic chips play a crucial role in photonic quantum computing. These chips integrate various components, waveguides, modulators, detectors, to manipulate photons. They enable quantum gates, entanglement generation, and quantum state preparation. 23. In summary, photonic quantum computing holds promise for practical quantum information processing, leveraging the unique properties of photons. Implementing photonic quantum computers presents several challenges. Let's explore them. Isolation and decoherence. To achieve viable calculations, quantum computers must be isolated from environmental noise. Reducing errors and delaying quantum decoherence when qubits lose their quantum state is crucial. Even with a small number of qubits, large cooling, wiring, and shielding infrastructure is necessary. 1. Fidelity at scale. Increasing qubit count while maintaining high fidelity is challenging. High-quality qubits are essential for complex algorithms. Achieving scalability without compromising fidelity remains a goal. Computation speed. Coherence time, how long qubits retain their quantum state, is limited. Gate operations must occur quickly to perform complex computations before coherence is lost. Multi-qubit networking. Linking qubits for gate operations enhances quantum computing power. Efficiently connecting multiple qubits is essential for implementing algorithms. Control over individual qubits. As qubit numbers increase, controlling individual qubits becomes complex. Precise manipulation of each qubit is critical for successful quantum computation too. In summary, addressing these challenges is crucial for advancing photonic quantum computing. That was all. Goodbye.